All right, good afternoon, everybody, and thank you so much for joining this seminar. In fact, we'll do it in hybrid mode. So we are excited to have with us Professor David Cebon and Dr. Parth Deshpande from the Cambridge University. In fact, David has visited us before as well. We just discussed probably that was 2017, right? And Professor David was also one of the reason because of that we have the center today. I still remember when he visited us at that point in time, and its discussion was all about trucking is one of the predominant mode of transport in India, and can we do something on the particularly road transport? And that was one of the point we thought about. Well, we have a lot of faculty who are excited to work in the road transport, sustainability. We are also our public systems group who are working in energy transition and so on and so forth. So can we put our efforts together and form the center? And at that point in time, I think we had some fascinating discussions, and post that we had multiple projects going on in this area. And today we are excited to have him back, and he'll be talking about decarbonizing the road freight in the UK. Specifically, a bit about Professor Cebon. He is a professor of mechanical engineering in Cambridge University, and he also is the director of the Center for Sustainable Road Freight and the Cambridge Vehicle Dynamics Consortium. In India, we talk about climate change today, but their team has been working on that for several years. And Professor also has many authored or co-authored papers on dynamic safety, energy consumption, and decarbonization of heavy vehicles. He's also the founding member of the Hydrogen Science Coalition. Along with him, we also have Dr. Parth Deshpande. He's a research associate at the Department of Engineering and Jesus College at the University of Cambridge. His research primarily explores technology choice models for road freight electrification from both engineering and logistics perspectives. And so we'll have two talks. Sometimes we have one. Today we have two. We are very fortunate. So first we'll have Professor David, and then we'll take up some questions. And then we'll move on to the second talk, and then we'll take some questions. And then we'll have tea and coffee outside. We can have some conversations there. Yeah? So thank you so much, Professor David. Please join us. So let's join our hands to welcome.
Thank you very much, Professor Roy. It's a great pleasure to be here again, although it's a bit too long since I was here. Should come a little bit more frequently. Going to talk about decarbonising road freight in the UK. That's because we live in the UK, but also because the UK should be one of the easiest places in the world to decarbonise road freight. And if we can't do it in the UK, then it's going to be very difficult in other places. And that's because the UK has quite a small country. It's a small country, small geography, large population, high population density, good road system, good communications. Everything should be good for the UK. So that's why it's a good target. Most other countries are more difficult, but I think we can learn lessons from the UK for other countries as well. Parth will talk a little bit more about some other countries also. So I'll just give a little bit of background. I'm going to talk about the low-hanging fruit. What are the easiest things we can do to decarbonise vehicles and logistics? Talk a bit about urban freight electrification, about long-haul freight electrification. Of course, what we call long-haul freight is rather short by Indian comparison, but still has the same problems. And I'm going to talk about 3 specific barriers to electrification and draw some conclusions. So there's 3 particular reasons why electrification is difficult, and I'll talk about those. So just a bit of perspective here. This is world carbon emissions in 2020. All the little bit at the bottom, 11% of world carbon emissions is road transport in the world, and about half of that is from road freight. So 12% of world emissions. So emissions from road freight is about 5%. Carbon emissions, but it's increasing, and it's increasing as other sectors decarbonise, and it's increasing as the amount of economic activity in the world increases, and as a consequence, more freight travels around, and they're pretty closely correlated. So we've got increasing amount of road freight in the world. Other sectors are decarbonising, and so we're going from 5% to maybe 10% by 2050 or more. 70 to 90% of businesses in the road freight industry are small businesses, maybe 5 trucks or less, family-owned businesses. Some are bigger, but a large proportion are small companies, and those companies have specific challenges, and particularly they have low operating margins, typically 3%, maybe 5% if they're doing very well. And those small companies have very little resources and expertise to put into decarbonisation, and they have, their problem is survival today. It's not how do we decarbonise in 10 years' time. So it's very challenging to decarbonise the industry simply from this organisational point of view, that you've got lots and lots of very small companies that are not really interested in decarbonisation. They make up the majority of the industry, and they have very low resources, limited resources. So that's challenging, particular challenging problem that we've got. So in terms of the low-hanging fruit, we can start with the easy engineering things. And we've been doing these things in the UK for some years, and some of this work happens in India as well. There's vehicle things like the aerodynamics and the tyres and making the vehicles lighter and so on. This driver performance is very important and shouldn't be underestimated. Can make a difference of maybe 15% of fuel consumption. So if you can have better drivers, you can reduce carbon emissions by 15%, which is a lot. Higher capacity vehicles are very important in general. The bigger the vehicles are, the more payload they can carry for lower carbon emissions. There's a whole lot of logistics factors, of course, as well. And they come from things like collaboration between companies, sharing information. Logistics is very much about an information industry, and by improving use of information, we can reduce empty running and reduce emissions. The relaxing time constraints, which are very important in European context, improving vehicle fill, making sure all trucks are full as much of the time as possible. So when you look at all those things and you try and quantify the emissions saving from them all, you can get to about 50%. We can cut emissions from road freight by 40 or 50% by doing all of those things. But we can't get to zero, can't get to nearly to net zero. And in order to do that, we need to change the energy source. And so these things are all very important, and they're increasingly important in the times of low emission vehicles. But we need to change the energy source, and the 3 possibilities are electricity, hydrogen, and biofuel. They are really the 3 options to go away from diesel and fossil gas. So I'm not going to talk about biofuel, except for what I say right now, and that is I'm going to rule it out. Rule it out because there is just not sufficient biofuel in the world to power all the world's trucks, not nearly enough to power the world's trucks. There's maybe enough to power ships or aircraft, but certainly not all 3, and certainly not enough biomass in the world to power the world's trucks. So ships and aircraft are much more difficult. They don't have the option for electrification. Whatever biofuels we've got left need to be used in those applications. But unless we can have a solution for the whole industry, it's not really a solution. We need to have solutions which can scale to the whole industry. As far as hydrogen is concerned, it's simply too expensive. There's all kinds of other things wrong with hydrogen, and I can speak about it spend most of the day talking about all those things. But the bottom line is that hydrogen-powered trucks cost twice as much as electric trucks and to purchase, and they cost 3 times more to operate. The energy costs are 3 times more. And when you have operating margins in the industry of 3 to 5%, it's completely ridiculous. There's no way that any fleet operator can afford to pay double. A hydrogen truck is double an electric truck. An electric truck is double a diesel truck. So the idea that you're going to pay 4 times as much for your truck and you're going to pay 3 times more to power it, it's just never going to happen. And those costs are determined essentially by the laws of physics. So I can explain that. So hydrogen is really not an option. Biofuels are not an option. We have to electrify trucking. That's the one way we can decarbonize. So I'm going to talk about electrification. So when we think about urban freight, this is a cartoon of the road network in the UK. So those roads are motorways. There are motorways. On the motorways are these big blobs, which are distribution centers, large logistics facilities, which are very important, and they tend to be located near to key nodes of the motorway network. At the ends of these roads are cities, and this is very schematic, but on the edges of cities are distribution centers, large supermarkets, urban consolidation centers. They all live on the edge, or they can live on the edge of the city. And so we can, in a way, divide transport by what goes up and down the motorways and what goes into the cities. Because in the cities, you can charge vehicles overnight at hubs on the edge of town. You can do multi-drop deliveries around the town through the day, delivering parcels or delivering food to convenience stores and city centre shops. You can transport rubbish, collect rubbish, and multi-drop and drop rubbish at refuse collection points. Now, all of this can be done by electric vehicles. It's all pretty straightforward. The vehicles can, and also buses and those kinds of passenger service vehicles as well. They can charge overnight. They can multi-drop during the day. Sometimes they can charge at charging points within the city. But overall, this is a done thing. I think the problem is solved. It's rolling out now, and it's building the technologies and supply chains for higher capacity vehicles for the future. So we'll look back in another 10 years and this will be done, and we'll say, why did we ever have those smelly, dirty diesel trucks, noisy diesels in our city centres, making all that pollution and so on. So I think this is going to happen. I'm sure that there's elements of this happening in India now. I know there's a lot of electric buses, for example, and I suspect that this, particularly because of air quality problems, it's air quality problems which has driven this over the last 10 years. And I think you've got similar air quality problems in India, and it's quite likely that that will be a driver of this kind of change as well. So we see that happening. As far as the long haul is concerned, the challenge is one of charging vehicles. So there's different ways you can charge vehicles. You could charge them at truck stops, something that looks a bit like this. We see these sorts of things for cars nowadays for charging electric cars, but this is a charging station by a company called Mylance, and you can see the idea. You've got a bunch of chargers. So you can do this on the motorway. It's a difficult thing to make money on. Truck drivers don't buy much coffee. They only have one driver in each one of these trucks. They take up the space of 10 cars, and they're sitting there on that piece of land for an hour. And so you have to pay for the land and the electricity and the whole facility, and you're not selling much coffee. So compared to providing diesel, which is quick and doesn't take up the land, and you don't have the throughput, this is a much more difficult thing to make work as a business model. There's other problems with it as well, though, and one of the problems, of course, with trucking is that it needs to be very reliable. You need to be able to charge very reliably, because if you can't, then you delay the vehicles and they miss their time slot, and they have a narrow time slot, maybe an hour, when they have to arrive with their load. And if they don't get there in that hour, then they miss the time slot and they have to come back some other time, and that messes everything up. So hitting the logistics slot is very important, which means that when you get to the charger, it's got to be working, it's got to be available, it's got to be able to deliver the amount of charge you need, and so on. And that makes it all a bit uncertain. And for those reasons, and the price is high, of course, for all those reasons, logistics companies are not very interested in that kind of charging, and they're much more interested in charging at the warehouse. And this is, a picture of a typical warehouse. And these warehouses, as I say, are at the nodes in the logistics network. And if charging goes on here, it has the advantage that the truck is typically on the loading bay for maybe half an hour or an hour. It's stopped anyway. So you can charge during this time without adding any time to the journey. And that's very important, because adding extra time adds cost. And if you want to fit the cost of the electric vehicle operation within the 3 to 5% profit margin that you've got, then you've got to do it in a way which doesn't increase the cost at all, right? It's got to be cheaper. So charging on the dock and the loading bay is very important. But you can see that this has got to tie in with the logistics. So there's a tight coupling between logistics and energy and vehicle performance here, which is very important to understand. And so it's very, very important for logistics people to be working with energy people and vehicle people to understand this problem, to work out how to solve this particular challenge. There are other possibilities. This is a battery swapping station in China. That's a Chinese battery, the big rectangular thing there. There's a lot of lifting equipment here and chargers, and the idea is you come along, take out the empty battery and you put in a new battery, and the empty battery gets charged up and put on another truck sometime later, maybe an hour later. So that's a battery swapping station. That's another possibility. Parth is going to talk about battery swapping. I personally don't think it's going to be a thing, and Parth will explain some of the reasons for that. I won't go into the details now. Another possibility is what's called dynamic charging, and this is dynamic. This is actually, I think, an AI image. I don't think this is a real image, but this is an AI image of a Chinese truck picking up electricity from overhead contact lines with these two pantographs. You've got a plus and a minus contact line. And you can put these systems along the main parts of the motorway. These vehicles have a battery, so that when the vehicle leaves the motorway, it can drop the pantograph and drive to the distribution center with a small battery. It doesn't need a very big battery at all. So it just needs a rather lightweight mechanism on top of the vehicle and a small battery. And this is a very efficient way, and we'll talk a bit more about that. We sometimes call this ERS, Electric Road System. ERS is an acronym that you'll hear. So, or dynamic charging electric road system is it? Yeah. This is another version of the same thing. In this case, the electricity gets into the vehicle through this conductive strip in the road. You can see it's segmented into 1 meter long sections, and they go plus minus, plus minus, plus minus, and they get switched on when the vehicle is over the top. So only the active segments are switched on, and the vehicle has two pickups, one that picks up from the plus and one picks up from the minus, and then gets rectified. Electricity gets rectified. So this is another possible dynamic charging system. An advantage of this system, of course, is that you don't have to be 5 meters tall to pick up your electricity. So if you want to charge a car or a van, then you could do it this way as well, not just trucks, and that changes the economics a bit. So There are two, I said there are three problems with electrification, three barriers to electrification. The first two are on this slide. The first is what I call a mass penalty. So in the UK, about a third of trucks carry heavy loads. And by that, I mean they carry liquids or bulk cement or bulk food, steel or aggregate, heavy loads, right? Only a third of trucks in the UK carry those heavy loads. The other 2/3 carry washing machines and sofas and clothes and cornflakes and potato crisps, lightweight things. So 2/3 of vehicles are volume limited, 1/3 are mass limited. For the mass limited vehicles, electric vehicles are a problem. And here's the statistics for the UK. In the UK, our maximum weight vehicle can carry 44 tonnes gross vehicle weight on 6 axles. And of the 44 tonnes, 29 tonnes is a payload. So all the rest is truck. All right, so you've got 15 tonnes of truck and 29 tonnes of payload. The biggest electric vehicles that we can run at the moment can carry 42 tonnes on 5 axles. That's already got a special 2-tonne allowance for electric vehicles. It used to be 40 tonnes on 5 axles. Now it's 42 tonnes for electric vehicles. But the payload is only 22 tonnes. And that's for complicated reasons to do with how the weights and dimensions work. So the loss of payload is 7 out of 29, which is a quarter, which is a lot. That means that you need 4 electric vehicles to move the same freight as 3 diesels. And that is a lot. That means that moving cement is going to cost you 33% more in logistics costs. The company has a profit margin of 5%. It can't afford 33%. There's no question of it. So no company with a profit margin of 5% is going to buy a vehicle, which means that it's going to have to pay 33% more and will make, therefore, 30% loss on that operation. That's not going to happen. So if this holds, at least for that 1/3 of vehicles, they won't transition. There is no way. If these conditions hold, there's no way for those vehicles to transition. The fleet operators simply won't buy the vehicles. Similar problem in China. To some extent, there's a similar problem in India. It's a slightly different one, but pretty similar. Of course, the big difference in India is much larger proportion of vehicles carry mass limited cargoes. And I don't know what the numbers are, but it must be 50, 60, 70% mass limit, 60%. My guru here is 60%. So, so this is 60% of the problem in India. There's also a time penalty. An electric vehicle can drive for 4 hours. The biggest electric trucks, you buy one from Volvo or Scania or Tata, it can drive for 4 hours, about 300 kilometers, and it has to charge. That means, and it has to charge for about an hour. 1 hour out of every 5, it's charging. That's 20% of its time. Now, in the UK, anyway, the drivers have to have a break. They have to have a break after 4.5 hours. So in principle, you could tie these things together. However, most of the rest stops in the UK occur during logistics stops. So mostly, the companies arrange it so that they don't stop vehicles out in the middle of motorway services on the highway, but they've got a security problem there, of somebody tampering with the vehicle, and they've got a loss of control of what's going on. The driver, if the driver stops at that point, they're going to add another hour to their journey. So you really don't want to do that. We schedule logistics so that the stops occur during logistics stops. So what that means is that you either have to charge the vehicle during the stops at the logistics facilities, And that means you have to have a large grid connection, electricity connection at the logistics facility has to be substantial because you got to charge all the trucks, right? Or you have to take an extra stop at a public charging point, which will cost 20% more because you're adding 20% to your logistics day. Right now, you've got to have 20% more vehicles to deliver the same stuff. So they're the problems. And so you're either going to have a large grid connection or you've got this time penalty of 20% additional cost. Okay, so what is the alternative? So they're the three things that the mass penalty, the time penalty, and the problem of providing charging in logistics facilities. Now, it's interesting to think about this think about two systems at once. We can think about static charging system that I've been talking about. We can also think about dynamic charging at the same time because they're really the same thing. The reason that they're the same thing is this. When you have a dynamic charging system, and here is a diagram of what it might look like in the UK, then you're going to have places like up here where you've got no dynamic charging because you can only afford to put dynamic charging on roads which have got lots of trucks. Because when you've got lots of trucks, you can sell lots of electricity and you can pay your investors back on the revenue that you're generating from electricity sales. So you can only do that if you have enough trucks on the road. If you don't have enough trucks, you can't possibly afford to put dynamic charging system on it. So you find the most heavily trafficked roads, and these are the ones in the UK, and there are places where vehicles are going to have to go on batteries. Now, and they've got some sort of radius of activity, and they'll have to have some static charging there. And of course, there's not just one of those, there's lots of those places around the country. And so you're going to have, even if you have dynamic charging, you still got to have some amount of static charges around the country. So there's an interesting question of how much dynamic charging do you have and how much static charging do you have? Because if you have a very large amount of dynamic charging, then we've got 200,000 trucks driving around this network all the time, any particular time, most of the time of the day, 200,000 trucks. So if you have a large network, then all those 200,000 trucks can have small batteries. And you don't need much static charging. On the other hand, if you have a small dynamic charging network, then all those trucks have to have big batteries and you have lots more static charging. And so somewhere in between those two, there's a sweet spot, which is actually the lowest cost operation where you have just the right amount of dynamic charging, you have small batteries in 200,000 trucks, and you have the necessary static charging as well. So it's interesting to think about that because it's solving both problems at the same time. So here's one way to do that. Here's three different dynamic charging systems, what we call light, medium, and heavy. So this has got the smallest number of dynamic charging roads. This has got a bit more, and this has got even more, and there's static charging as well. And we can collect data, logistics data from our industry partners about the journeys that they're running. And we can simulate those journeys and think about what would happen, what electricity would be used on such a journey, right? So here is the journey. The black line is the speed profile measured with a telematics system. The red line is the elevation, right, going up and down hills as it goes along. So this is 16 hours, two driver shifts. And then this is the battery. The battery starts off full and then it empties out. And then at this point, there's a drop off and the battery stays still for a bit while the vehicle's stationary. And then it runs out a bit more. And then it charges here at a rest stop and so on. So you've got charging and discharging and so on. And we can see here that the maximum size of this battery is about 400 kilowatt hours. That's what you'd need to do this journey. So we can look at any journey that we get from logistics data, from telematics data that comes from one of our industry partners, and we can assume a set of charging arrangements, and we can calculate how big a battery you would need for that journey. All right. So when you do that, here's what you get. So here's one journey. This is from one of our partners. They're called Operator H, and this is London here. This is the south of England. London is here. It's got a road called circular road, the M25 goes around. And this is the top of that. The journey starts here, goes out to the west and does a drop off. Then it comes back to the depot and goes down to the south and does a drop off, comes back to the depot and then goes all the way up here and does a drop off and then comes back again. All that takes 18 hours. So this is 18 hours in the life of one truck. And operator H said to me, "You're talking about electric vehicles. This is what we have to do. How are you going to do that with an electric vehicle?" Okay, so let's look at how we're going to do that with an electric vehicle. What are the possibilities? If we took that electric vehicle and charged it overnight in the depot at this red point here, and then we wanted it to drive all day, 18 hours, to do all of this, then it would need a 1,666 kilowatt hour battery, 1.7 megawatt hour battery. The biggest battery you can buy in a truck today is 600 kilowatt hours. So this is about 3 times bigger than any battery you can buy in a truck. Okay, so that's clearly not going to happen, at least not for some years until batteries are a lot better than they are today. So, but it can't happen today. If you charged at the drop-off points for 40 minutes at 600 kilowatts, so quite high-powered charging, then the battery size would come down to 400 kilowatt hours, which is plausible. You can buy a battery like that. It's expensive, but you can buy it. If you charged at the public rest stops, the driver does have to have a break, and he has a break at these 2 points. If you charged at those points only, you would need an 800 kilowatt hour battery, which again is significantly bigger than anything you can buy. And this one is when you put these things together. So if we have the electric road system, then the light electric road, there's the M25. These are the roads that the light electric road is on. And you can see that on this bit of the journey, there is an electric road, nowhere else. And what that does is cuts down, if you just charge overnight plus the electric road, then you need 1 megawatt hour battery. So that's a bit more practical. This is looking a bit better. If you can also charge at the drop-off points, then you can manage with a 240 kilowatt hour battery, which is the size of a battery in a bus. The biggest buses have batteries about that big. If you charge at the drop-off points, at the rest stops, then it doesn't change it. And so it goes. If you have the medium ERS, you can see there's ERS down here, all the way around there. The heavy one has got ERS almost everywhere that this vehicle goes. And you can see what happens to the batteries. In some of these cases, you get down to, well, this is the most significant point. If you don't have any other charging other than charging up at the warehouse and driving on the ERS, you can do it with a 220 kilowatt hour battery. And at 220 kilowatt hours, the drivetrain is not very much heavier than the diesel. So you can, the diesel engine and gearbox and fuel tank all comes to about the same weight as a 220 kilowatt hour battery and electric motor, and inverter. So that's the most significant thing, that with this electric road system, you don't have to stop to charge at any point. So you just do the logistics as you do today. And the weight of the vehicle is about the same as the diesel vehicle. So you can carry exactly the same stuff as you carried before. And all of those 3 penalties, the time penalty, the weight penalty, and the electricity connection problem, they all go away. And I'll explain about the electricity connection problem now. So electricity connection problem is that if we're going to do this stuff, charging at these points, we've got to have a warehouse like the one I showed with lots and lots of trucks lined up, and it has to have a big enough electricity connection to power all those trucks. And that may be a very big electricity connection, really big enough to power a town. So how many of those do we really need? This is a graph showing all the warehouses in the country, 28,000 warehouses, 6,500 retail stores, 14,000 factories. These are all facilities that need probably some amount of electricity. Now, we can we can try and estimate how much electricity they need. This is a Google Map, Google Earth picture of a warehouse, and you can see trucks lined up at the loading bays here on both sides of this warehouse. So this is a really huge warehouse. And we can, from the database of logistics facilities, which is a government of commercial properties, which is a government database, we can find out the area of this building and its GPS location. So we know how big it is, and we know its location. And we can look at similar buildings again with Google Earth, and you can count loading bays, right? We can count how many are on this. So if you go to 50 different logistics facilities or something, you can count how many loading bays they've got. How many loading bays they've got. You can plot that on a graph against the area of the facility, which we know from the government database, or in fact, you can measure it, and you can plot this kind of graph. And you can see there's a strong correlation between the number of loading bays and the area of the logistics facility. So big logistics facilities need lots of loading bays. Now we know we can make some assumptions about how much time vehicles spend charging and how much each loading bay is being used. And when you do that, our estimate is that there's about 10,000 facilities in the UK that are greater than 2,000 square metres. That's the size where we think they'll need a significant grid connection. And when you look at the electricity requirements, it's somewhere between 4 and 20 megawatts in those locations. So 10,000 locations where we need 4 to 20 megawatts. Now, if you actually go and try and ask the electricity company for a grid connection of 20 megawatts, they'll say, don't be ridiculous, because it's such an enormous connection. You know, you can power half of Ahmedabad on 20 megawatts. But even 4 megawatts is a huge amount of electricity. So what we're talking about here is 10,000 places where you've got to ask around the country, where the owner has got to put in a big electricity connection in order to charge trucks, and they're probably someone else's trucks. The person that owns the warehouse probably isn't the person that is driving the trucks. So out of the goodness of their hearts, some 2,000, 3,000, 5,000 different companies have got to go and spend millions of pounds to put in electricity connections to put sufficient electricity into 10,000 warehouses. This is a very big problem. Right, there's a queue for electricity connections that's 15 years long in the UK at the moment. In some places, not 15 years long everywhere, but in some places 15 years long. So just simply putting electricity connections in to solve this problem is just enormously challenging. And I suspect it's probably just the same in India. So this is a summary of the warehouse charging, right? Here's where we are. If we do warehouse charging, we've got to make a grid connection. Here's a picture of our warehouse with all the trucks lined up out the front. It's got a 4 to 20 megawatt connection, maybe 50 fast chargers in it. And every one of our warehouses has got to have a similar kind of connection, right? So there's lots of these, 10,000 of them around the country. They're not all as big, but there are many big ones. So summary here. If you just have this kind of system with no dynamic charging, you've got to have big batteries. We've just seen the sizes of the batteries that you've got to have. You've got to have big batteries. That's a big red battery there. You've got to have 10,000 at least electricity connections. You've got to have high-cost vehicles as a result of the battery. This is the most expensive part of the vehicle. You've got a reduced payload. You've got the mass penalty that comes with it. And you've got something between 10 and 25% more trucks as a result of the mass penalty that you are suffering there. So this is not great. It's not a great picture. So if we do it with dynamic charging, things are a lot easier. This is a map of the motorway, the light the light ERS network. You can see the dark lines are the light ERS network. This is that M25 around London again. This is just the bottom of the country. The grey lines here are the electricity transmission lines. So these are the big power lines go across the country. So we've got one here, for example, just outside of Cambridge where Parth and I live. This is called the A14, this road. And in the middle of and it crosses this big power line, and it's a farmer's field, right? This is a place outside of the city centre where this big motorway is travelling, and you've got the electricity grid going past. If you were to put a substation there, that orange dot, that's a substation. It's about, looking at the colour, about 250 megawatts. That substation would power the ERS from this triangle here to this triangle here. And then there's one there, which is about the same size, which would power it from here to here. And there's one there, which is probably about 100 megawatts, which would power it from here to here. So you can go around the whole network. You can say, for this light network, how many of these connections would I need? Because this is an easy thing to do, or relatively easy, right? Because it's a farmer's field. It's out in the countryside, and the power is right there. So you just essentially drop a connection right down, build your substation, and then you can power along the road with private wire in both directions. So if you do this, it turns out that you need 60 of these connections to do the entire light ERS network for the country. So instead of 10,000 electricity connections, we need about 60, plus some static charging, a small number of static charging connections. So that's a much easier problem to solve. That's a centralizable problem, and it can be solved in one go by private industry or by government. So where we end up with this is you have one big grid connection like that. There's maybe 50 or 100 of them in the country, and they power a wire which goes along the motorway, and you have these what are called traction power units which feed in to the motorway and connect to the dynamic charging system. So much smaller number of grid connections, less than 100 of up to 300 megawatts. So they're much bigger connections, but there's a small number of them, and they're localized. You have small batteries in 200,000 trucks. So all these trucks now have small batteries. You have low-cost vehicles as a result. They can carry a full payload, so you don't have any mass penalty, you don't have any time penalty, and so you do logistics as per today. So this has everything going for it. Everything going for it as a strategy, including the cost. And just very quickly, this is the total cost of ownership. Parth will show you some better graphics in a minute, but this is from 2030 to 2050. Total cost of ownership in the 6-year first life of the truck. So we buy a truck, we run it for 6 years, we sell it, subtract one from the other, add the energy cost, but not the driver cost. Driver cost not added, and that will be about £400,000 for a diesel truck. So there's a diesel. We don't know what's going to happen to diesel fuel and cost of diesel fuel in future. We're just going to assume it's constant because we might go up and it might go down. We really don't know. So that's the total cost of ownership of the diesel with time. This is a hydrogen fuel cell vehicle, which is way too expensive and will never catch up. This is a 900 kilowatt hour, 1200 kilowatt hour battery, 1.2 megawatt hour battery, probably won't catch up with diesel either. This is the rate at which we think battery costs will come down and vehicle costs. And these are ERS vehicles. Here is a 300 kilowatt hour ERS vehicle. You can see that from 2030 onwards, it would essentially be cheaper than the diesel vehicle to run already. So importantly, if transport costs more than diesel cost to run, somebody has to pay for that. It can't be the logistics operator. Logistics operator's only got 5% to work with. So not going to pay double for the cost of logistics. So that ultimately has got to be the taxpayer, the government, the consumer, the public are paying for this. So the public, either through their taxes or through some other mechanism, have to pay for this. Alternatively, if you can go cheaper than diesel, then that gives you a bit of headroom that you can charge a bit of tax. You can tax the heavy vehicle industry without changing their profit margin. Their profit margin is the same at this point along here. So you can collect some tax. And of course, at the moment, the UK government anyway collects a lot of tax from diesel fuel duty. And that's going away, and they've got a bit of a problem. What are they going to do? Where are they going to get that tax from in the electric vehicle world? So because these vehicles are more efficient, they give you headroom for tax. We think they'll be cheaper than diesels to run. So I'm going to skip over this. This is a summary of the whole thing. Just conclude. Battery electric vehicles are available now, but with substantial payload loss. Electric logistics is doable with time and weight penalties and something like 10 to 25% increase in logistics costs because of those penalties, time and weight penalties that I mentioned in the UK. It's different in other countries. Charging is the problem. Truck stop charging is necessary, but is not nearly sufficient. Our government at the moment thinks that it just puts in some truck stop charges and that solves the problem. There's no way it will solve the problem. You need to have some. When vehicles get into trouble, they need to be able to charge somewhere, but it's not going to be the main method for charging. Warehouse charging is essential for reasonable journey costs. We will have to have charging in warehouses. You need about 10,000 electricity connections if you're just going to do static charging, if you're not going to have any dynamic charging. And that is very challenging and is a potential blocker. It potentially can stop the whole thing from happening. The combination of electric vehicles and electric road system is the lowest cost, the lowest carbon, and the lowest weight. It reduces battery size by somewhere between a factor of 2 and 4, which is substantial. It eliminates loss of payload for mass limited trucks, which is 60% of them in India. Logistics is essentially as now. You don't have to worry about charging time. There's headroom for tax recovery by the government, and it eliminates most static charging and about 10,000 large grid connections. And just one final thing to say, and that is that these cost penalties must be overcome. They have to be overcome for widespread rollout of electric vehicles. If we can't get those penalties to zero, the fleet operators simply won't buy electric vehicles. They'll keep running diesels, and the electric transition won't happen. If we want the transition to happen, these penalties, the mass penalty and the time penalty and the grid connection problem, these three problems have to be solved. Otherwise, there's no transition. So that's where I'll end up. It's just one more. Solving this problem, it's not a logistics problem. It's not a vehicle technology problem. It's not an energy problem. It's all of them mixed together. If you want to tackle this problem, you have to have a multidisciplinary team with energy people, with vehicle people, and with logistics people. That's the only way to solve this problem. Thank you. So I'd be happy to take a few questions quickly. I don't know if there's any online.
I have one question. So even for the dynamic charging, right, there's a huge infra cost for putting that. And that's quite expensive too, right? And that is quite inflexible because once you put it there, I'm not sure who can use it. Are we losing space of that road? I don't know.
You don't lose space on the road, no. So Parth will present some more detail on that.
Okay.
When you look at the total cost of the whole system, the electric dynamic charging system is significantly cheaper than static charging system. the infrastructure is very high utilization. Right? It's used all the time. And you compare that to static charging, in warehouses where you've got lots of chargers which have to be available, but which are only getting utilized a third of the time or half of the time or something like that. So you have many more of these grid connections, which are very expensive and low utilization resources. Whereas with the dynamic charging system, we have very high utilization and then much smaller batteries, so it's cheaper vehicles across the country. So in terms of the total cost, it's by far the cheapest. But it is also the case that the infrastructure can be funded by private finance. There's a good enough business model, just as there's businesses that are building static charging systems. They think they're going to make money selling electricity to cars and trucks. The business model for selling electricity by dynamic charging is better, right? Because you don't have the land, you don't have the low utilization assets, you don't have nearly as many grid connections, you've got much more concentrated capital cost base. So the business cost is better. If you were to run a company to do dynamic charging compared to static charging, you would do better doing dynamic charging. So it's privately financeable, and Path will show you that. And the business model is better.
Got it.
Okay.
Any other questions, please?
Good afternoon, Professor. Myself, Dilip. I'm doing food and agribusiness management in Ahmedabad. Quick points I need to add it to your system in that, okay. One thing I thought is this dynamic system has been carried in German, I guess. DHL has done some pilot run with Scania for their logistics, and I guess. And one more thing is, what are these drivers expecting during the halt? Let's say they're going for a halt in somewhere. Are they taking risks? Apart from that, what are the other activities that they want to do with? So that we can come a kind of an ecosystem built around it, like a shopping activity, kind of food activity, or a stay or a lounge access, like whatever we can provide. Because in India also we have tried a part where we have a system called Dabas, where you have a halt station there where you can have all this eateries and kind of small refreshments and whatnot. And so how can we build a kind of ecosystem around it?
Yes. Well, you're right about that. Siemens and DHL and so on, that Siemens have had the overhead contact lines running for about 10 years in 3 different test sites in Germany, and they've run very well with no problems. But they're having trouble getting it rolled out. The German government doesn't want to spend the money to roll it out, and I think that's the case. Most governments don't understand the problems, and they don't see why they should roll out this infrastructure, and that is a challenge. That's why I think it actually has to be done through private investment. People don't seem to understand that actually it's a better investment than static charging. And there's billions and billions of dollars going into static charging around the world. People pouring in money. Public and private partnership. I'm sure there is. It's certainly challenging because the motorway is owned by the government essentially. So there's an ownership. You're putting some private assets on the government facility and so on. There are challenges working out how to do all of that, but ultimately the numbers, the physics and the economics are that it's cheaper, and it's the only way that we're going to get it done. There's certainly issues around truck stop provision for drivers and making a much better ecosystem for drivers. I think there are many truck stops in UK and Europe which have quite good facilities for drivers. Often the facilities in the warehouses are terrible, and they're the places where drivers have got to stop, to spend time, and that could be improved a lot as well.
Good afternoon, sir. My name is Sai Shankar Iyer. I am pursuing AGMP from IIM Ahmedabad. My question is why we are targeting, say, long haul comes with itself or lots of challenges, like infrastructure has to be done and many if and buts are there. a large amount of investment and so on. But why can't, is there a possibility where we capture the low hanging fruits, such as the ports operation, where a long haul truck or a big truck has to just operate 10 to 12 kilometers just to take the container and put it somewhere else, or in fact in mining operation also, where from the core mining part he has to just deliver up to a certain 10-15 kilometers away. So those track, the 10-15 kilometer track can be dynamic charging can be available there, and prove the concept and then scale it up to the long haul system.
Yeah, well, that's an interesting one. Of course, those trucks can easily be static charging as well, right? You can easily do those electrically, and they're the obvious targets for particularly port operations. I mean, mining as well, but there's fewer of those. But the port operations, port hinterland, charging at the port, and of course you still have a mass penalty, right? And we can't carry a full container, for example, on an electric truck in the UK. So you get a container which is 29 tons, you can't carry it. So you have to put on the diesel. So there is a problem there.
So static electricity is not working in port and mining right now. Why? Because the vehicle works for 18 hours continuously, non-stop. So they don't have the leisure to stop in between for static charging.
Yeah.
So if we employ dynamic charging over there, the load implication might be there.
Yeah.
So we can increase the efficiency. So is this kind of situation, the port and mining, anywhere in the world we are implementing this
Yes.
kind of charging right now?
Yes. So there are mining operations with dynamic charging systems. And in fact, Siemens, for example, and Alstom, that's where they're focusing their attentions first, because you don't need a government to give you permission. The mining company can give you permission, and you can provide them with a lower cost service. So they're the things that they're starting with, because they've not been successful getting governments to move. The real challenge is to build that first section of dynamic charging on a highway, and it's a business challenge as much as anything else. And the real problem is that if you only have a short section on the highway, then it's fine for vehicles that just drive up and down that highway. But as you'll see in a minute, you need about 2,000 of them a day to make it pay. And so to have 2,000 vehicles just driving backwards and forwards, you don't have that. You have motorway sections, but those vehicles drive everywhere. So there's very little incentive for them to put a pantograph, to have that kind of technology, when it's only going to help them on 1 out of 50 routes that they do a day, or do in a month. So the real challenge is to just get an economic way of getting that first route to work. So that's the problem at the moment.
I guess in most of the Europe and UK, I guess the most of the logistics operator own the most part of the trucks. So once they want to adapt to this new technology, what is the point? Like, how can what are the existing vehicles that's been owned by these logistic operators or the carriers? How can it be called back by, or like, what is the resale value? How they are going to write it out? Then that becomes a next challenge, because they own in hundreds and thousands. Let's take DHL or like Maersk or Hapag-Lloyd, like whoever owns this many fleets.
Yeah.
How are they going to change or adapt to this one?
Well, so those big companies, they buy new trucks every year, and they'll turn over a fifth of their fleet every year or something like that. Now, over 5 years, they've got a new fleet. So they'll be buying new vehicles, and they can just as easily buy electric vehicles as they can buy diesel vehicles. And if those electric vehicles have a pantograph or on the roof or a pickup so there's no real problem for those companies, the rich companies in Western countries, the rich carriers. It's no real problem for them. The only hurdle is that when they buy that vehicle, it's got to be as profitable as the diesel that it replaces, right? And as long as you can satisfy that requirement, they'll buy an electric vehicle with a pantograph just as well as they'll buy anything else. So that's the sort of trivial answer, right? It can be just done as part of the fleet replacement, but it's a much more difficult problem than that. Obviously, it's a problem because of you know, the 90% of vehicles which are run by small companies, where that may be more difficult. It's a problem because of in many developing countries, the fleets will buy second-hand vehicles, or in fact, in the UK as well, fleets will buy, you know, second life vehicles, and you don't get a secondary market in electric vehicles until they, you know, that lifetime has happened. So you're not going to have. So it's much more complicated than what I've said. There's a case for retrofitting electric vehicles, or even retrofitting diesels, making them electric. So there is a complicated problem of that market dynamics. But at the simplest level, you know, the companies that are buying new trucks can buy ERS trucks just as well, if you can make it profitable for them.
Also, sir, one more question. Like, if hypothetically, let's say, if UK government is ready to give a complete electrification with dynamic charging and everything, is this companies like Volvo's or Scania's are ready to just modify the existing vehicle so that the loss can be, or rather than getting a completely producing a new vehicle, just can put an pantograph in the existing vehicle and change the engine module or something? Is it possible that?
Well, you can change. You can put it. They're willing to put it on an electric vehicle. So if they have an electric vehicle, they can do one with a pantograph just as well. They're not. The OEMs are not that keen on dynamic charging. Why not? Because it means that they sell vehicles which are cheaper, smaller batteries. What they want to do is make as much money as possible. So the biggest battery they can sell, the better. So the OEMs are not all that enthusiastic about this. If the first thing you do when investigating dynamic charging is go and ask the OEMs, you won't do it, because they'll say, no, we don't think that's going to work. It's not in their interests. So I don't start with asking the OEMs. I start with logistics companies, because when logistics companies see the challenges of putting in electricity connections in their warehouses and the payload loss that they get and the time loss that they get, then they're looking for some other, you know, anyone who actually wants to transition needs a different solution to what's being proposed at the moment. Yeah.
The technology changes quite fast, because every few years we are seeing new thing.
Yeah.
So is it that a barrier for adoption of such any kind of these things? Because
Is it-
I'll just wait for the next wave, and maybe next wave is even cheaper. So
Well-
I postpone decisions.
Okay, well, so that's an interesting point. We're trying to take that into account. The most likely change, the thing that we know that will happen, is that batteries will get cheaper and energy density will improve. Okay, that's what we know will happen. So will they get cheap enough? I mean, the cost of EVs will come down, so that's for sure. Will batteries get small enough that the problems get big enough, small enough in mass, big enough in energy, so that the problems go away? Well, maybe. The problem that might go away, you might, with fantastic improvements in battery performance, you might get to the point where you could put a 2 megawatt-hour battery on a vehicle with no payload loss penalty. I doubt it. I mean, it's a huge change from now. But even if you did that, you still have to charge that battery, and that battery will take exactly the same amount of energy as the vehicles today. All right. So if we need that electricity from 10,000 locations, which we need now, you still need electricity. You still need to put the same amount of energy into the vehicle. So it may be that you have a smaller number of locations. Maybe it's 5,000 locations, but now instead of needing 20 megawatts, you need 40 megawatts, right? You need double the size of grid connection. So you need just the same amount of electricity, whether or not the batteries. Now, you could say, well, we'll have something else other than electric vehicles. I don't know what that will be other than, you know, nuclear aircraft or something. I don't see that there's going to be any solution other than that. So whatever happens to electric vehicles, we still need to provide the electricity. We still have the problem, which is the real problem of providing electricity at these warehouses. And it's still much easier to do with dynamic charging. So dynamic charging system is not going to become obsolete. If it's there, companies will use it and it will become the default system. It won't become obsolete at all.
So we have a few questions.
Good. Right. Right. So thanks, Professor Rai, for introducing me at the start. If you already forgot, I'm Parth Deshpande. I work with the Center for Sustainable Road Freight at Cambridge, which is why I forgot my voice as well. So ignore that. Sorry for that. But yeah, I'll be picking up on what Dave presented today, and specifically 3 points. One is that electrification is necessary for decarbonization. Then there are 3 blockers, as we just saw, and then ERS can solve some of them. So there's those 3 key points, and I'll take those and I'll go into a bit more technical detail about these 3 points. So just to start off, we saw that, well, worldwide road transport contributes to quite a lot of emissions. In the UK as well, there's very few HGVs compared to cars. By HGVs, I mean heavy goods vehicles. And of the total transport emissions, 96% emissions in the UK are due to road transport, of which 22% are due to HGVs. So that's a fairly large number considering the population in the UK. And the rest is then light duty vehicles and passenger cars as well. So the emissions are disproportionate, is what I would call them. And it's not just a UK problem, but it's a global problem. And we can see that based on the amount of road freight, the amount of growth in road freight that has happened over the years. So in countries like China, India, and so on, road freight has gone up over the years. In a few other countries, it's gone down slightly as well, maybe because of shifting trends, manufacturing locations shifting to countries like India and China and so on. So we need to have solutions that work globally, because currently there's a one-fits-all solution. Everyone uses diesel trucks in all countries. We need to have a solution that is based on electrification, that can solve the blockers and can work globally. Now, is this actually possible? Well, we can only try to find out. And so what we do in this presentation is try and build some technical models, some techno-economic models, to try and answer a few of the questions and take into consideration the blockers as well. So what are the blockers? Again, just to recap, one was the grid connections. They're expensive and complex. There is a backlog in several countries. The other was the charging downtime penalty. We need to stop and charge, which costs money. And not just money in terms of driver costs and vehicles, but also freight delays, and there may be penalties and so on. And the third one was the payload penalty. So as David mentioned, there's the batteries need some space. They have a certain mass, and we have therefore a payload capacity loss in the truck. That's because of regulations surrounding the total length of the truck and the loading on the axles. So for example, here is a standard 3-axle tractor unit that's sold in the UK. That's a diesel tractor unit. It can carry a trailer that has a payload of 29 tons. Whereas a comparable battery electric vehicle can only carry 22 tons. So it's one category lower than this one because it has a missing axle. And the space that was taken up by that axle is now being taken up by the battery. So that's where the batteries are located for the electric trucks. So, and also, like, you can't just extend these to the back and have a battery there, because the total length of the truck is limited to 16.5 meters in the UK. So there's no possibility of doing that. You're stuck with this one. So also in terms of the options, we saw that obviously static charging has to be a primary solution. You still need chargers no matter what you do. That's similar to what David showed us, a static charging site. You need that in lots of logistics facilities. Could do battery swapping, which can save time, but it can have queuing issues, and that's something I'll discuss in a bit more detail in a bit of time. There's also issues surrounding interoperability because when we talk to OEMs, they don't want their batteries being swapped with other OEM batteries because they maintain the secrets. You have the coolant in the battery that's specific to an OEM, they design the formula, and you don't want mixing happening. And they're expensive and complex. I'll show you some costs of these stations. They're super expensive, super complex to build. There's something new here. I call it Pony Express, which is quite funny. So instead of swapping the battery, what if we just swap the entire tractor unit out? When you run out of battery, park the tractor unit, take a new one out, and then be on your way. Now, it sounds that it might be more expensive. It doesn't sound quite right, but I'll show you why it's actually better than battery swapping. And finally, electric road systems that David showed, they could be overhead ones, so they could be in-road ones, and I'll discuss those as well in a bit more detail. Of course, grid connections are a lot easier with these. Right, so I was talking about a one-fits-all solution like diesel. Could we do something like that? So there's so many different pathways that it's very hard to achieve economies of scale like we do with diesel trucks right now. So can we have a modular system that will work everywhere, and you can choose the energy source based on the requirements of logistics and so on? That's what it would look like. The base drivetrain of the vehicle would be an electric drivetrain, and you can change the energy source based on what are the resources available. So you can have an electric drive that's powered by either big batteries, and it can use static chargers or battery swapping. You can use a range extender. So what if you just remove a battery pack, add a little engine in, it becomes a hybrid vehicle, and use biofuels in cases where there's no charging available. Or you can use electric road systems with it. You can just retrofit a pantograph or another sort of pickup and use ERS with it. So this is sort of the solution we focus on, and we try to develop models for each of these bits and compare them. To do that, there's a need to develop a simple journey model. So obviously you have a lot of complex models. You might have studied agent-based models and the like of those. They're very big and complex, and it's hard to understand what's exactly going on. So we tried and develop a simple journey model to understand what is the increase in logistics time due to charging stops. So how do we quantify the charging downtime penalty? So if we have a journey that looks like this, going from origin O to destination D, so the journey length is L, we can look at it in terms of the battery dip. So the battery dip is the change in state of charge of the battery going from full to empty. And that defines what is the size of battery that you need for that journey. So I have a 0.8 times Bmax there because OEMs limit battery dip to 20% state of charge. So you can't discharge it more than 80% because that damages the battery. And so if we didn't have any charging along the route, it would just go down. That's the maximum battery size you need. But you can't have that big a battery size if you're going a long distance. So you'll be limited by what is the size available in the vehicle, which means that at some point you need to stop and charge. So naturally, what a driver would do is they would stop, they run out of battery, they stop, they charge it up to full state of charge, be on their way again. They run out of battery again, and they need to add another charging stop until the last one. So in the last charging stop, you only need to charge enough to reach the destination, because otherwise you're just like waiting there for no reason. And so that's the sort of model we use for calculating the time increase. Here's an example of how it works. So we call it the fundamental diagram of logistics as well. So for an example journey of length 400 kilometers with 300 kilowatt chargers along the way, we also add a 10-minute overhead time. So that's the time required for the vehicle to actually come to a stop, plug the charger in, and then after charging, again, remove the charger, be on the way. That's what the time increase looks like. So in this plot on the x-axis, we have battery size, the size of battery in the vehicle. The y-axis is the percentage increase in journey time. So how much extra time is needed because of charging compared to the base travel time. If there's no charging, you need a very big battery. There's no time lost as well. So that's good in terms of that. If you wanted to use a smaller battery, you would need to add a charging stop. Now you could change the duration of that charging stop. So you could say that, okay, I stop for longer or I stop for a small amount of time. That changes the battery size requirement. And that also changes the increase in journey time. at some point with that one charging stop, you reach a full battery. So if you stop for more time, you're just waiting there without charging the battery. And there's also a little step there because that's the overhead time, the 10 minutes that I mentioned. And so then you can add another charging stop somewhere in between the first one and the end of the journey. And that helps you bring the battery size down further. And you can keep adding charging stops. So that's the graph that tells you what is the increase in journey time because of charging. And we can use it in an interesting way. So I'll come to that in a bit. So there's some good examples, but we can use it to calculate the total logistics cost. So as David mentioned, the increase in journey time due to charging is an important factor in the logistics cost. And instead of using TCO, we developed this new metric called the total logistics cost. So if you went to industry and sort of tried to establish whether electric vehicles are feasible, what they would do is they would just look at the total cost of ownership. So that's the cost of the vehicle, cost of the energy over a certain time period. And they say, okay, electric vehicles look good that way. But when you ask them, are you actually using an electric vehicle? They'll say no. And you ask them why? That's because there's a payload loss and there's the charging downtime and so on. So they can't actually use them in practice. So we thought that there should be a metric that quantifies all these penalties within one factor instead of using the TCO. That's the total logistics cost. It's better than the TCO. And it considers the consequences of these two penalties. So it looks something like this. That's the total logistics cost. It consists of the vehicle cost split per hour. Depending on the battery size, if you have a larger battery, it is higher, otherwise it's lower. You add to it the driver cost per hour. Then we have a factor that gives us the extra vehicles that we need due to the charging downtime. Multiply it with that. There's another factor that considers the payload loss. So if you have a certain payload loss, you need extra vehicles to carry the same amount of freight. It has that factor as well. And we multiply it with the total travel time because it's costs per hour. We also add something called end charging time. And that's based on the concept that if you, for example, took a rental car out through, well, there's Zoom car in India, I think. If you took a car out, I don't know how it's in India, but in the UK, you need to return it with a full tank. You need to fill up the tank and then return it. And we use the same concept here because if you're using some energy during the journey, you need to account for the time spent in charging up the battery to full at the end of the journey as well. Otherwise, you're losing that penalty. That's accounted for in there. We then add a factor called freight value of time. So that is a penalty added to this cost based on how urgent the goods are. If they're very urgent, it's high, otherwise it's zero, goes off. We multiply that with the amount of payload and the journey time. So that's like a penalty factor. And then obviously the running costs, so the cost of electricity from public chargers and warehouse chargers, cost of diesel and cost of using electricity from electric roads as well. So that gives us the total logistics cost. How do we use it? So here's a quick example. What if we, instead of just one journey, had a distribution of journey lengths? So this is some data from the UK. We have a probability distribution of journey lengths. We can use this and run a Monte Carlo simulation to then find what is the total cost of logistics for different battery sizes. And that's what it looks like. So the x-axis is the battery size. The y-axis is the total cost. I do it per kilometer because their journeys of different lengths. That's the total cost curve added up for all these journeys. That's the components as well, just for reference. So that's the standing costs, that's the freight value of time, and the energy costs. And you see that there is an optimum there. So that's if you wanted a truck that could do all those journeys, what is the battery size that you would choose? Well, it's that one because that results in the lowest average cost for that sort of journeys. So this is a quick, nice and easy application of this total logistics cost. Now switching themes slightly towards dynamic charging, because as we saw, it does a good job of solving most of these barriers, most of the barriers to electrification. We can look at that in a bit more detail. This was a study on the cost break-even dynamics of electric road systems. Essentially, what is the time required for you to get your money back on a private investment? And this is what the money looks like. So the x-axis is the time in years, the duration. Y-axis is money. You have two curves there. One is for the expenditure, and one is for the income. We have a brief period at the start, that's 5 years, that's construction time. So during the construction time, you're installing the electric road, so there's no income, but you've started spending on it already. It takes 10 years. We assume it takes 10 years for it to reach peak usage, from no one using it to everyone using it. That's accounted for there. And then there's a commercial loan as well that we assume, and that goes off after 30 years. So this point where these two curves intersect, that's the break-even point. And that's what we focus on. We want to have returns within a certain number of years. And this is assuming that there are 3,000 trucks per day on the road. So this gives us a way to correlate the number of trucks on the road to the break-even duration and the overall economics of the electric road. So we'll use this going forward. Of course, the finance cases may be different. So I just showed you an example here, but you can vary all these parameters: the construction duration, the ramp-up duration, the break-even duration, the loan, and the interest rate. So we have 3 different cases. Case A is the quickest return period, but it has the highest interest rate. Case B is sort of a moderate case. And when we talked with a few investors who we asked, well, would you invest in the ERS? They said, maybe. And we asked them, what would be your conditions? And they said, case B. So that's like the more realistic one. Case C is the more relaxed one. So it takes you a long time to get your money back, but lower interest rates. So we'll be using these throughout the presentation for all the results. But what we can do using these is try and correlate the economics of the electric roads with the economics of the vehicle. So I showed you 2 things. I showed you the total logistics cost, that is from the perspective of the vehicle. And I showed you the cost break-even model for the ERS, that's from the perspective of the infrastructure. Now, how do we link those? So first, we need to make some assumptions. I assume that we use an ERS vehicle that has a 250 kilowatt-hour battery. 80% of the journey is on the ERS. So there's 10% at the start and 10% at the end that's not on the ERS. We assume that the payload requirement, the demand is 29 tons, so that we are looking at the worst case scenario, like what if you want to carry a mass limited payload. And the ERS sizing depends on demand. So it depends on the traffic flow. If you don't have many vehicles using it, you'll put in a smaller substation. Otherwise, you'll put a larger substation. And we include all the standing costs as well. So this plot is the big one. It correlates the 2 sort of perspectives. And the x-axis is nice and common. So the x-axis tells you what is the cost of electricity that's being sold from the electric road system to the road user, to the truck operator. The left-hand y-axis is what is the total number of trucks on the road per day, per lane as well, so in one direction. The second y-axis is what is the total logistics cost of that vehicle with respect to a diesel vehicle. So you can see that diesel is at 1 because we're dividing by the cost for that. And then for the ERS truck, it increases as you increase the cost of electricity from the ERS because it's going to be more expensive to run the truck. And if we look at the left-hand y-axis, we see the 3 different curves there. They correspond to the three different finance cases, A, B, and C. So A was the quickest returns, C was most relaxed, B was moderate. And if we then go back to the right-hand y-axis, now we want to ask ourselves, what is the maximum cost of electricity that could be charged from the infrastructure to the vehicle so as that the logistics would be profitable? Well, it's that. So we just look at the point of intersection. So that's 28 pence per kilowatt hour. If we go back down to these curves to look at what is the daily traffic flow per direction, we get corresponding to A, it's 5,000 trucks per day, B is 3,000, C is 1,700. And that there is the base price of electricity. So that's the cost of electricity that's charged to the infrastructure provider from the grid. And what remains is the profit margin. So case B, which I said was the most favorable one for investors, has a requirement of 3,000 trucks per day. And that's the answer to the problem. But as David mentioned, there's one more key point there, which is that you could possibly charge a tax. So governments earn a lot through diesel fuel duty. I mean, even the Indian government imports diesel, so they earn a lot through that. Now, in this case, because we have a sufficient profit margin, we could just add a tax margin to it. And for case B, it would go from 3,000 trucks per day to just 6,000 trucks per day. So being required for cost break even. So there is the possibility of adding that with electric roads. And I'll show you in a minute why you can't do that for static charges as well. if we look at a map, so that's a map of England, all the roads in green, they're the ones that have more than 3,000 trucks per day. So these are the ones where electric roads are feasible. And this is the same as the medium ERS network that David showed us. So it is privately financeable, and you can still have a margin for government tax. It is profitable for the truck operator. Their costs are cheaper than diesel, and the infrastructure can earn its money back. If you look at India, there's not much data available for traffic counts. So I've put in terms of traffic flow, but this is just to highlight the key roads in India that have the highest amount of freight flow. So there's Mumbai to Delhi, there's Delhi to Kolkata, Kolkata to Chennai. There's this one going from Delhi to Nagpur as well. And these are the ones that have the highest amounts of truck flow and where ERS could be profitable as well. Right. What if we can't have ERS? So what if we don't have more than 3,000 trucks per day on the road and we need to use static charges? What are our options? So yeah, I'll be comparing some of these options. Now to do that, we need to be careful in accounting for the cost of infrastructure. So the cost of infrastructure is, well, we think it's easy because, well, it's just the cost of one charging unit. There's two other things that are key that we try to incorporate. One is the cost of land. And to do this, I used an approach that was similar to the one David showed us for the warehouse, for counting the number of bays. So in this case, we do the same thing, but we do that for a truck rest stop. So that's a truck rest area in the UK, and that's a parking area just next to a rest stop. And we calculate the total area that's required for that, including maneuvering, count the number of parking spots. And I say that, well, for every 3 parking spots, you can have 2 charging stops. The reason is because if you look at the sort of arrangement, so you could easily park 3 trucks in the space that's needed because you need some space for the charger between 2 charging spots as well. And if we do that, we get a nice correlation between the cost of land and the number of charging spots, and we can use that to do our calculations. The other important thing is the cost of grid connections, which are super expensive. So we used a couple of different sources for that, and we developed a model for that. You can see that it's not linear. It goes up a lot as the size of connection increases. That's because the complexity increases. You need more components, you need more wiring, you need more safety equipment, and it's complex to install. So it goes up quite a lot with large grid connections. So these are the 2 costs we use, along with obviously the cost of the charger itself and so on. Then we did a cost break-even model, exactly the same as that for the ERS, but for static chargers. And we got some good results. So this is one of the results. This assumes that if you're looking at a certain number of events per day to achieve cost break-even, we assume that each event is for a fixed amount of time. So we're looking at 3 different charges. So on the x-axis, there's the electricity profit margin. That's the sale price of electricity minus the wholesale price of electricity. And the y-axis is the usage per day that you need for cost break-even. And we're looking at 3 different charges. So there's 300 kilowatts, 600 kilowatts, and 1 megawatt. If you say that they're each being used for 30 minutes at a time in an event, the economics look pretty similar because you use the faster charger for the same amount of time. It's more expensive, but you're selling more electricity in the same amount of time. So they all look almost the same. Whereas if you look at a different type of event, if you look at a fixed energy usage event, so if you wanted to sell 600 kilowatt hours of energy from each charger, the economics would be vastly different because now they're selling the same amount of energy, but the 1 megawatt charger is much more expensive than the 300 kilowatt charger. So that was one good insight that we found. And then we went back and tried to link this economic model to the vehicle costs as well. So same as the electric road systems model, we had different costs for chargers depending on the number of chargers in the set because the size of grid connection varies and the cost of land varies as well. So that was the basis we used for calculating this and the total cost of logistics as well. So we get something similar to the electric road scenario. So that's the cost of logistics for the diesel truck at 1 because it's with respect to diesel, and that's the cost for the static charged electric vehicle. And you see that they never intersect. So it's impossible for you to do the same logistics with a battery electric truck that you could with a diesel truck, and for some values of cost of electricity, you could do that for an electric road systems truck as well. So they never intersect. Now it's just not possible. What we need to do then is add a cost penalty or add a subsidy. So you could do either or. I chose to do the cost penalty. If we added a 70% cost penalty so that they intersect, we get a certain value for that, which is 17 pence per kilowatt hour. And then we can go back to our finance cases and look at the daily events required for you to achieve that finance case. So we're going to keep this in mind, the number of events required for each finance case, because I'll be showing the results in comparison to the other options a bit later. But the key takeaway here is that it's not possible to do the same logistics at the same cost. And there's no room for a tax margin because, in fact, the government has to then give out a subsidy for the electric truck. We can do the same for battery swapping as well and for Pony Express. But just before that, I'll explain how we developed a sizing model for the battery swapping station. So that's what the battery swapping station looks like. Assume a hypothetical scenario where the station has 3 chargers. Let's say battery is charged within 15 minutes and it takes 5 minutes to swap. We use this to develop a methodology for how many chargers and how many batteries should be inside the station. So the way it works is, let's say at just before t equals 0, there's a truck that has come in, it has swapped a battery. Battery is now being swapped. It's called B1, and it has to be plugged in to charge somewhere. At t equals 0, we say that, okay, there's this battery that has come in, we plug in to charge a charger C1. Now, assuming all the others are fully charged, we take B2 out, and then there's the next truck that has come in for 5 minutes, and it's being swapped with B2. Now, there's a new battery that has come in B2. Let's say we put it in place of B3, take B3 out and swap it, and then so on. We do the same for B4 as well. Now, it's been 15 minutes from t equals 0, which means that B1 has fully charged up, because in this hypothetical scenario, I assume that it takes 15 minutes to charge the battery. So for the next round, we can then take B1 out. So B1 was in the station for 15 minutes of charging. It took 5 minutes to swap. If we divide these numbers, 15 by 5, that's 3, which means that we need 3 chargers and 3 plus 1, that is 4 batteries, 4 spare batteries inside the swapping station. So you can do the same calculations for when it takes actually 1 hour to charge the battery and it takes a bit more than 5 minutes to swap. You just divide those numbers, that's the number of chargers, and plus 1 is the number of batteries you need. So that's how the full system works. Now you may think it works beautifully because it takes like 5 or 10 minutes to swap. It's much faster than charging. But there's another issue with it, which is queuing. Yeah, I'll just skip through this. Yeah, the queuing. The issue with queuing in this is that there's only one service lane. So unlike a static charging area where you have 10 different chargers waiting, ready to be used at any time, with the battery swapping station, there's just a single lane. And if you've studied queuing theory, you may realize that, well, that's a bit of an issue because that's going to result in a long queue. And so we can use that to compare the average delay in the system. So that's what that looks like. So we look at how many hours is the system in continuous use for at the peak arrivals rate. And we can look at the average delay in the system for the queue. And we can do that for the battery swapping station, and we can do that for the charging site as well. So with the battery swapping station, the average delay builds up quite quickly because there's one service lane. If you have more vehicles coming in, they have no option but to wait. With a static charging scenario, if there's more vehicles coming in, they can just use an available charger. And so there's diminishing returns if you have a long amount of time where the station has peak arrivals rate. So the whole point of battery swapping was that it is quicker to get energy, and you can use that to pay for the extra cost of the swapping station. But then if you start having issues like queuing, it's not going to be possible in 5 minutes. You're going to need more than that. And so no one's going to be using it then. And in fact, when we were in China, we spoke to taxi drivers there and asked them, well, do you use battery swapping? And then the guy was like, yeah, well, we used to, but because of queuing issues, we stopped doing that, and it's just quicker to go and top up at the charger. So that's the other big issue. Of course, there's issues such as the cost of the station itself, and so on, and interoperability as well. Now, I spoke about Pony Express briefly. So what if you swap the tractor unit out? It turns out that you can do that a bit cheaper. And the reason is that if you look at the cost of extra tractor units that you need, plus the cost of chargers at the charging site where you'll be charging these tractors, it's the exact same as the cost of extra batteries needed in the swapping station, plus the cost of the swapping station building, the whole mechanism. So there's cost of the crane, there's the cost of the automation system. It's fully automated, so it's super expensive. Can cost up to £1 million for one station. They can do it for cheaper in China and India. In the UK, it's going to cost £1 million, and you still need chargers and a grid connection and everything else inside the station. That's going to be the same. So the cost of these extra trucks actually matches the cost of the extra batteries and the swapping station. That is £1 million. And so you could just park the tractor unit, put it to charge, and then take out a fully charged tractor unit and be on your way. There's no need to install a battery swapping station and swap the batteries out. And that was quite an interesting revelation for us. Of course, it will need some rearrangement of logistics, because then issues arise such as who owns the trucks, what happens after you swap them, do you just leave them, someone has to take care of them, and so on. And we can calculate the cost benefit of this by looking at the charging downtime penalty. So we get rid of the downtime penalty from the driver. So the driver keeps moving, only the tractor unit has stopped, and the freight keeps moving as well. So the freight value of time constraint goes away. The extra driver cost goes away because of charging time. But we do keep the downtime penalty for the tractor unit. Now, if we just compare these using the same analysis and look at the number of events you need, number of charging events or swapping events you need per day for the same finance cases, assuming the same 70% cost penalty over the diesel vehicle, we can see that, well, for static chargers, if you had 10 static chargers, you get a certain number of minimum required charging events per day for the different finance cases. Gets lower as you go along because that's the more relaxed finance case. You can look at what if I put fewer chargers in. That makes it a bit better because you don't spend as much on the capital cost. We can then compare battery swapping to it. Battery swapping with 600 kilowatt hour batteries, that's a bit better than static charging. And it looks better here, but that's not accounting for the queuing issues and the interoperability issues and so on. Battery swapping with smaller batteries looks pretty similar to the larger battery case, no significant advantage. Whereas Pony Express is, again, a bit cheaper than battery swapping. So by cheaper, I mean it requires fewer events to achieve the same finance case. So it's a sort of win-win situation because there's no queuing issues. You don't, you get better finance scenarios, and you don't have to build a complex swapping station with all that expensive equipment. So that's another important conclusion apart from the ERS one. Now, very quickly, what happens with technology improvement? So that was a question that was just raised, which was, well, what happens as batteries get better and better? Will ERS returns diminish? So we tried to look at that by looking at what is the estimated decrease in the cost of a battery pack over the years. What is the estimated decrease in the cost of the electric vehicle, excluding the battery? So we assume that would also decrease, not just the cost of the battery pack. And battery weight would also decrease. By that, I mean the energy density would increase over the years. So these are the assumptions we made. Of course, there's an uncertainty band because we cannot predict the future. But we use that and sort of try and predict how vehicle costs would change. And we do that in terms of the total cost of logistics. So some assumptions, we look at journey lengths from 10 kilometers to 800 kilometers and take the average. We assume a payload requirement of 29 tons. That's what you carry right now. That's what you want to be able to carry in the future. And all the costs are in current pounds. So don't worry if you don't see the diesel costs going up because there's no inflation accounted for. It's just in current money. That's what that looks like. So the x-axis is the year. Y-axis is the cost of logistics with respect to diesel. So again, diesel is at 1. The blue curve here, that's for a battery electric truck that has the same battery capacity as today. That's 600 kilowatt hours. And if you maintain the same battery capacity, the range will be the same, but the weight will reduce, so you can carry more in the back of the truck. There's another scenario, which is that as batteries get lighter, you might want to maximize your battery capacity to get more range out of the truck while keeping the same payload capacity as current electric trucks, which is 22 tons. So that's another scenario. And then this is a scenario of a hybrid range extended vehicle if you had a small engine on board to power the vehicle when it runs out of battery. And this is the ERS vehicle with a small 250 kilowatt hour battery. So what we see right away is that the ERS vehicle becomes cheaper than diesel sometime between now and 2030. And it remains cheaper and by a huge margin. So we saw that the profit margins of logistics companies are like 3 to 5%. So it's well below that. And so you can have charge a tax on it as well. All the others are higher than diesel. And it's important to note that in the UK, at least, there's going to be a ban on sale of IC engine trucks from the year 2040. And none of these are cheaper than diesel at that point. So there's going to be no push to switch to them, which means that there will have to be subsidies. The government will lose a lot of money. And then even after that, people will still face the same issues. So the payload penalty and the charging downtime penalty, these two penalties will still remain even if you had like much better batteries than now. And that's based on our predictions. And of course, the grid connection issue gets worse. As David mentioned, you need even larger grid connections to charge these massive batteries. Right, that's the 2040 year. Cool. So just to conclude, we looked at a metric called the total logistics cost or total cost of logistics, what do you call it, which considers the payload and cost penalties, which are both significant issues. So it's better than just using the TCO. We saw that the ERS is profitable with a cheaper cost of logistics than diesel and leaving room for government tax. We saw that even with technology improvement, the benefits of ERS will still be quite significant. Where it's not possible, we saw that among the other options, Pony Express or tractor swapping, or I think in India you call it a horse. So swapping the horse would be the best solution, of course, with some considerations around de-engineering logistics. If there's no chargers at all, then you need to use a range extended hybrid vehicle where you can use biofuel. So we said at the very start, David said that there's not enough biofuels to power the whole trucking industry. We can use them in scenarios where there's no charging possible, and that would be a very few scenarios. In terms of what to do next, we want to do more specific case studies. We need a lot of data for that. We got some data for the UK, which is why we show UK results. But getting data from other countries is quite difficult, and that's something on our radar. We want to develop some more complex models. So we started with simple models to understand the problem. Now that we have an understanding, we can go on to more complex models. And we want to look at weights and dimensions changes to try and solve the payload penalty issue. And of course, look at this in different countries as well. Just like to acknowledge several people that have supported this work, including Professor Cebon, who's been advising this work, all the people who've worked on different projects that supported this, including the SHUB, all our international collaborators, and all the companies that either paid money or sent us their data to use for the study. And that's it from me. Thank you.
Actually, you mentioned all the cost on infrastructure, but you never include the climate change. Or what happened if it's high rainfall, otherwise high snow? There is no cost. And also maintenance. Vehicle maintenance is very important, especially during the catastrophe.
Yeah.
You never include that cost.
We have actually included maintenance costs in this. So I haven't been able to show it explicitly because of time constraints. But so we have included maintenance in two places. One is where I show the electric road systems model, the income and expenditure, that one. The expenditure includes the maintenance cost. That's a fraction of the total capital cost, and which is why even after the loan ends, you still see an increase in the expenditure. That's coming from the maintenance. So we have a detailed model running behind the scenes there. And in terms of the cost of logistics, the vehicle cost per hour factor, that includes all the things such as vehicle depreciation, how long is the vehicle being used for, maintenance costs, duties, vehicle duties, excise duties, and yeah, the driver cost includes driver wages. In the UK, there's something called national insurance contributions, and so it's all sort of hidden behind the scenes. This, yeah.
Also, the map route. I just wonder.
The England one or the India one?
England. Okay.
Yeah.
So these are actually the electric chargers, right? So I wonder actually how it's work. If one of the roadway is black, can we detour?
If you're using electric roads, you mean?
Yeah,
Um,
especially in the natural disaster, whatever happened, that road blocked, what else we can do?
I mean, so in terms of resilience, actually, electric roads are much better than charging because, first of all, there's fewer grid connections. So it's much easier system to take care of in the case of natural disasters. In terms of flexibility, the ERS is very modular. So if there's one section of it that's damaged or switched off, you can just like not use that bit and sort of you could also detour, but even if it's switched off, you could just continue along the same road. You could retract your pantograph. So for example, if you have an in-road ERS and there's snow on the road, you just switch off a little section of it. You still have a small onboard battery, so you have a 250 kilowatt hour battery that can take you over that section, or if there's a detour, then along that route, and then you can join back on the ERS. And the pickup also is retractable, so for all kinds of ERS.
Okay, thank you so much.
Yeah. So we have some questions from the online participants. The questions are addressed towards both of you, so either of you can answer. No, we don't. We only have one. What is it? So the first question is, in India, cities like Kolkata have tram lines that have been largely unused for several decades now. Could such existing infrastructures be modified or recycled to support dynamic charging electric road systems?
Yeah, I mean, in Kolkata especially, trams are mainly based inside cities. They're in urban environments. Electric roads, as David said, they benefit from longer distances and highways. So it's unlikely the same infrastructure could be. Well, you could obviously then remove it and reuse it somewhere else. So yeah, it's not the same locations. What could be reused is the learnings, especially from electrified railways. So like India has managed to electrify most of its railways. Compared to the UK, it's not that much. And so the same learnings, it's the same sort of project. The same learnings could be applied to ERS as well.
Thank you. Another question in line with what you said is, alongside road trucking for freight, what is your view on shifting some of the freight to other models like the rail for freight transport?
Yeah, I think that's obviously desirable because rail freight transport is much more efficient than road freight transport, but it's not as flexible as road freight transport. And so you can't deliver to remote locations. So you will still need trucking even with intermodal transport, even with rail transport, that'll be intermodal transport. And there's the other issue with capacity as well. So in most countries, you have railways, but they're at capacity with passenger transport. So it's quite hard to shift all of the freight demand onto the railway system.
Thank you. One last question. Based on your initial impressions, could you provide recommendations for developing long-haul electrification in India, given the wide variation in road quality, width, and geographical terrain?
Road quality is a challenge, but
Yeah,
you can see that the roads that are carrying the most truck freight are the big motorways and the big highways. And I haven't travelled on them all, but I think that they're generally the better quality roads. So I'm not sure of the answer, but I think most likely those roads will be okay for dynamic charging systems.
It is on the national highways.
Right. So Rishabh says 70% of Indian freight is on the national highways, and I guess the national highways are pretty good quality roads, so should be okay.
Another question that lies in the same this is that as in India, most roads are designed to accommodate mixed traffic. So will development of dedicated lanes for access to dynamic charging cause a congestion in the road traffic?
Well, there's two things. One is the installation phase, and obviously during installation there will be some disruption, although I think part of what we're trying to do is work out how to do the installation very quickly and efficiently with minimum disruption. but during operation, it's just the same as it is now. It's just that, all the trucks would travel in one lane, which is what happens in Europe anyway. And in a way that can reduce congestion because you have all the slower moving traffic in a disciplined way in one lane and all the faster traffic in the other lane. So that's probably a good thing. Decongest.
You won't need a dedicated lane essentially. It'll be a normal lane on the motorway for the highway.
The last lane is
But all the HEVs drive in the right-hand lane in India anyway. So, yeah.
So it would improve lane discipline and probably reduce the traffic problems.
So one last question. Are there any data sets or information available detailing the power and energy consumptions by trucks and ERS systems like load profiles?
Well, yeah, we know a lot about that. So it depends on what the question is, but we know that a normal truck needs about 150 kilowatts to drive on the highway. And it depends on the weight and the aerodynamics and the tires, but on overall about 150 kilowatts. So we think that you would size the ERS system so that it could deliver 300 kilowatts. So you would have 150 to drive the truck and 150 to charge the battery. So that would give you an overall. In terms of the overall power, at the other end, that's one truck. In terms of the overall country, when we do calculation for the UK, we find that if you power all the trucks with electricity, that you need about something like 10 to 15 gigawatts of power. Now, that compares to currently the total power consumption of the country is about 30 to 32 gigawatts on average, if you average it out throughout the whole year. So you're going to add a third to a half increase the power consumption of the country to power all the trucks on electricity. And that is significant. That's a significant increase, right? A third to a half increase in overall grid capacity. But we compare it with the other things that we have to do with with the energy transition. For example, we have to convert all our heating systems to electric, to heat pumps and so on. We need to convert all of industry from fossil fuels to electricity. And that's expected to probably double the amount of electricity that we need in the country. So we're talking, it's recognized that we'll have to double or more the total electricity capacity in the country. And of that, about a third to a half, we're going to have to go from 30 to about 70 gigawatts, and about 10 of that, 10 or 15 will be trucking. So it's a lot, but it's not crazy.
Thank you. So that about covers all the questions from our online press.
All right, let's thank Professor David and Dr. Parth for coming to IMA and giving this fascinating talk. It was totally electrifying that way. No, I think it is also telling a lot about the progress that we are making in electrification. And I think even in India, a lot of things are happening. So thank you again for giving this fascinating talk and visiting the campus. Thank you so much. Thank you.